In this lesson, we'll look at applications of trig functions. As we go through this lesson, you'll notice that for each of the questions, we can use a trig function to model the relationship between any two variables that have a periodic relationship. Our independent variable x does not always have to be an angle. Like in the first question, we have a relationship between the height of a rider on a Ferris wheel and the amount of time that they have been on the Ferris wheel for. And then this function relates the rider's height to the amount of time they've been on the Ferris wheel for. And there's a periodic relationship between those variables, which is why we can use a trig function, in this case sine, to show the relationship. And part A of this question says to graph this function using transformations. Well, I notice it is a transformed sine function, so I may want to start by making a table of values for a normal sine function. I'll pick some key points. I'll choose values within one cycle of sine x, so I'll choose values between 0 and 360. And then I could find the corresponding y values by doing sine of each of these values, either using a calculator or using your unit circle. On the unit circle, remember the y coordinate of where the terminal arm intersects the unit circle tells us the sine ratio of that angle of rotation. If I look at the y coordinates as I rotate counterclockwise around this unit circle, my y coordinates go 0, 1, 0, -1, and then back to 0. Which is why the values for the sine function go 0, 1, 0, -1, and then back to 0. Now let's do the transformations that we have in the equation. Notice we have an a, k, d, and c that transform this function. I'll make a table of values for this function. We'll start with the horizontal transformations. K is 3, which is a horizontal compression by a factor of 1 over 3, so I would have to divide all the x values by 3. And then the d value of 30 shifts it 30 to the right, so I would have to add 30 to all the x's. And then for the y values, the a value of 10 does a vertical stretch by a factor of 10, so I would have to multiply all the y values by 10. And then the c value of 12 shifts it up 12, so I have to add 12 to the y values. I'll take all of these x values, sub them in for this x to get my transformed x values, and then I'll take each of these y values, sub them in for this y, and then calculate my new transformed y values. And now plotting all of these points will give me one cycle of my transformed function. So I'll go ahead and do that. Now, like I said, this is one cycle of the function, so that cycle is going to repeat over and over again. This is a periodic function. So if I were to just imagine this cycle continuing to the left, I know that it's going to get down to the min when x is 0. So it'll be at a y value of 2 when x is 0. If you're not able to see that pattern, what you could do is just take our equation that tells us the height at any given time we want. And you could sub in 0 for the time and calculate your height. And it would give you a value of 2. But let's go ahead and answer the following questions, where it says determine the max height, the min height, and the time for one revolution. Well, the maximum height I can see is up here at 22. And the minimum height of the rider is down here at a height of 2. And the time for one revolution? Well, that would just be the horizontal length of one cycle. If I highlighted one cycle between the min values, the amount of time it takes for the rider to get from the bottom of the Ferris wheel up to the top and then back to the bottom of the Ferris wheel, well, it takes from 0 seconds to 120 seconds. So it takes 120 seconds, or we could say 2 minutes. And now part C says to represent this function using a cosine function. The equation it gives us is a transformed sine function. Any sinusoidal wave we could represent as either a sine or a cosine function. The only difference is going to be the d value, the horizontal shift. For a cosine function, the d value is just the x coordinate of a maximum point. Here's a maximum point. Its x coordinate, if I look down, is 60. So what I can do is I can just take this function, rewrite it exactly, but change the d value to 60. So I'll go ahead and do that down here. And now this new equation and the original equation that the question gave us, they both model this graph exactly. They're both equivalent equations. And to demonstrate that to you, in part D, it says what is the height of the rider after 35 seconds? Use both equations to verify your answer. So I'll use both the sine and cosine functions to find the height at 35 seconds. So for each of the equations, I'm going to sub 35 in for t and hopefully get the same answer for both of them. All right, starting with the cosine function, I suppose you could type that in exactly as it is on your calculator, or we could evaluate it step by step. I have 35 minus 60, which is negative 25, and then that needs to be multiplied by 3 to give us negative 75. And using your calculator, you can get an approximate value for that of about 14.6 meters. And now let's try the sine function. 35 minus 30 is 5. Multiplying that by 3 is 15. And then evaluating that on your calculator, you'll get the same answer of 14.6 meters. And looking at the graph, we can see that when the time is 35 seconds, that would be about right here. If I connect up to my function, it looks like somewhere between 14 and 16. So our answer of 14.6 seems to make sense based on the context of this question. Now let's move on to our second of 4 application questions. This one, it doesn't give us the transform sine or cos function. It just describes the scenario that has a periodic relationship and will make the equation. It says that skyscrapers sway in high wind conditions. In one case, at t equals 2 seconds, the top floor of a building swayed 30 centimeters to the left, which we're going to represent with negative 30 centimeters. So the negative just means from its neutral position, it has gone 30 to the left. And at t equals 12 seconds, the top floor has swayed 30 centimeters to the right of its neutral position, which we represent with a value of plus 30. Let's model this relationship with a cosine function that describes the motion of the building in terms of time. So our independent variable, once again, is time. To write a transformed equation, I know I'm going to have to figure out what the a, k, d, and c values are that could transform the cosine function. And notice once again I'm using t instead of x because my independent variable is time. Let's start by solving for the a parameter, which corresponds to the amplitude of the function, and we can calculate that just by finding half the distance between the max and the min. And that's what the formula, max minus min divided by 2, will calculate for us. Its max value is going to be positive 30, and its min value is going to be negative 30. So I'll do 30 minus negative 30, and then divide that by 2. 60 divided by 2 is 30. And then to calculate the k parameter, we do 360 divided by the period of the function. Well, we know that it is at the min value at 2 seconds, and it's at the max value at 12 seconds. So if we think back to what a sinusoidal function looks like, let me just show you the previous example. The horizontal distance between a min and a max is just half of the period of the function, right? The full period is from the min all the way until it gets back to the min. So if we know the horizontal distance between the min and the max, that is only half of the period. So in this question, the amount of time between the min and the max, so between 2 seconds and 12 seconds, is 10 seconds. That's half of the period, which means the full period is 20 seconds. So the k value is 18. C is like the average value, so the average position of the building. And we can calculate that by finding the average of the max and min values. So add the max and min and divide by 2. 30 plus negative 30 divided by 2 is 0 divided by 2, which is 0. And lastly, the d value for a cosine function is its x value of a max, or in this case, the time of a max. Well, at 12 seconds, it's at its maximum value of positive 30. So the d value for cosine is 12. And now I can write my final answer. And then part B says, what is the equation of a sine function that describes that motion of the building? So I want to write an equation that is equivalent to this, but using sine. And we haven't made the graph, and I did that intentionally because we need to know how to be able to do that without the graph. And the only way you'll be able to do that, let me remind you, if we have a sinusoidal function, the c value is the midline of the function. The d value for a cosine function is the x-coordinate of a max. So if I know the x-coordinate of this blue point, that is the d value for cosine. If I want the d value for a sine function, so the horizontal shift of a sine function, I need the x-coordinate of this point right here. This is what we call a rising midline. It's where a rising line intersects the midline of the function. And the relationship between these 2 points is that they are always 90 divided by the absolute value of k apart from each other. So if we know the d value for cosine, we can just subtract 90 over k, and that will give me the d value for sine. And since our d value for cosine is 12, let me apply this. The d value for sine, I can take my d value for cosine and subtract 90 over the absolute value of k. So in this question, that would be 12 minus 90 divided by, what was our k value again? Our k value is 18. Well, 90 over 18 is 5, and 12 minus 5 is 7. So I can write my equivalent sine function by rewriting this exact same equation, except change cosine to sine and change this 12 to a 7. So I'll do that below here. And there we have it. This function that I just highlighted there, and this cosine function up here are equivalent functions. They describe the same relationship between those two variables. And now let's move on to our third example. This one says the height of the tide on a given day at t hours after midnight can be modeled with this equation. Now, if you don't know how the tide works, well, the tide goes in and out throughout the day, which means the depth of the water at a given point is going to be going up and down periodically throughout the day. And this function tells us that periodic relationship between the height and the time where t is hours after midnight. Part A wants us to find the max and min values for the depth of the water. Well, in this transform sine function, I have my a, k, d, and c parameters that transform the function. I know if I want the max height of the water, I can just take my c value and add the amplitude, which is the absolute value of a. So in this question, that'd be 7 plus 5, which is 12. And I'm not sure the units the height is in. It might be meters, but it doesn't give us in the question, so we won't assume. The min height I can get by doing c minus the amplitude, which is the absolute value of a. So 7 minus 5, which is 2. The shallowest the water is 2, and the deepest is 12. Part B says, at what time is high tide and at what time is low tide? Now, there are a couple ways we can do this. We can think graphically, or we can just solve for it algebraically. If we're thinking graphically, maybe I'll just go up to this diagram that I drew right here, and we can use that to help us figure it out. Well, since I have a transformed sine function, I know this d value of 5 would tell me the x-coordinate of a rising midline. So let's replace d sine with 5. And also in the equation, we know the k value. The k value is 30. So I can replace this k value with 30, making it 90 over 30. So the horizontal distance between these points is 90 over 30, which is 3. Which means if there's a rising midline at 5, moving 3 to the right, there'll be a maximum point. So there'll be a maximum point at a time of 8, which is 8 hours after midnight, which is 8 a.m. So there'll be a high tide at 8 a.m. And there'll be another high tide. If we move the period of the function to the right, there'll be another high tide. Well, what's the period of the function? We can calculate the period by doing 360 divided by k. And I'll actually make a note of that here. Our k value is 30. 360 divided by 30 is 12. So the period is 12 hours. So if there is a high tide at 8 a.m., 12 hours later, on a 24-hour clock, time would be 20 hours after midnight, which is 8 p.m. So I can state there is a high tide at 8 a.m. and 8 p.m. And now what about low tide? Well, if 3 units to the right of a rising midline, there's a high tide. 3 units to the left, there will be a low tide. 3 units to the left of 5 is 2. So there would be a low tide at a time of 2, and then again 12 hours later, when time is 14, which would be 2 p.m. So at 2 a.m. and 2 p.m., there would be a low tide. So we were able to get those answers without actually solving anything algebraically. But let me show you how we could use algebra to solve for this if you wanted to. So I'll leave these as my final answers because I know that's what I'm going to get, but let me show you how we could get those algebraically. When solving for the high tide, I'll start by rewriting this equation, but setting the height of the depth of the water to the max depth, which is 12. And then if I wanted to solve at what time is the low tide, I would rewrite this equation, but set the height to the min height, which is 2. And now I just have to solve both of these equations for t, and I should get the first answer for both of those equations, and then use the period to find the second answers. Let's start with the high tide equation. I'll start by subtracting the 7 to the other side, and then this 5 that's being multiplied by the sine function, I can divide that 5 to the other side, so I'd have 1 equals sine of 30 times t minus 5. And now I have a sine function equal to 1. Well, if I know my unit circle, let's look back up. I drew it way at the beginning. If I know my unit circle, I know the sine ratio is equal to the y-coordinate of where the terminal arm intersects the unit circle. And if I rotated 90 degrees, I would be at a y coordinate of 1. So I know sine of 90 is equal to 1. So therefore, all the way back over here, I know that if this was 90, then this sine ratio would equal 1. So I can just set this argument equal to 90. If you didn't fully understand that unit circle explanation, you could also just say that this angle would be equal to the inverse sine of the ratio that it's equal to. And inverse sine of 1 is going to give you 90 if you ask your calculator. And then to isolate t, we would divide this 30 to the other side, and then add this 5. And you can see that we ended up getting a final answer of t equals 8, which matches this answer of 8 a.m., 8 hours after midnight. And then because the period of the function is 12 hours, there's also a high tide 12 hours later at 8 p.m. And then I can follow this same process for solving this equation. Subtract the 7, and then divide the 5. And then based on the unit circle, I know that sine of 270 is equal to -1, so I would want this angle to be 270. Or you could just set the angle equal to the inverse sine of this ratio of -1. Divide the 30 to the other side, and then add the 5 to the other side. And we actually get 14 hours after midnight, which is 2 p.m. So we actually got the second answer first, but that's fine. We could just subtract the period to get the first answer of 2 a.m. So now that you know a couple ways to find the time of high tide and low tide, hopefully you feel comfortable with at least one of those two. And let's move on to part C, which says, what is the depth of the water at 9 a.m.? Well, that's an easy question. We have an equation that tells us the depth of the water at any time we want, so I can just replace this t with 9 and then evaluate. So I'll go ahead and do that. And then using a calculator, you could get an approximate value for this, and you would figure out the depth of the water at 9 a.m. is about 11.3 meters. And now let's move on to our very last question. It says a wind turbine has a height of 55 meters from the ground to the center of the turbine. Graph one cycle of the vertical displacement of the tip of a 10-meter blade turning counterclockwise. Assume the blade starts pointing straight down. So I guess let me start by drawing a rough picture of what this wind turbine looks like. Now keep in mind, it's not going to be a great picture, but it'll be enough for us to figure out how we're going to be able to graph this. All right, there you go. We have a windmill that's sitting on the ground. I know that it says from the ground to the center of the turbine is 55 meters. So let me label that distance. And I know that each blade is 10 meters long. So the min height of the tip of the blade, I'll put a green dot on there. The min height of that green dot as this spins around is 55 minus 10, which is 45 meters. But as the wind turbine spins, the tip of this blade represented by that dot there, it's going to spin up here to its max height above the ground. And since the blade is 10 meters long, it's going to be 10 meters above the midline. So 10 meters above 55, giving it a max height of 55 plus 10, which is 65. And what we're going to do is we need to graph the vertical displacement, so basically the height above the ground, of the tip of this blade that starts pointing straight down. So our y-axis is going to be height, and our x-axis, we don't know anything about time for this question, so we'll just use angle of rotation for our independent variable. And I know at the start, since it's pointing straight down, it's going to be at the min height of 45 when it hasn't rotated at all. So when the angle is 0, the height is 45. When it rotates 180 degrees, it'll be up at the max. It'll be up at 65 when the angle is 180. And then once it rotates a full 360 degrees, it'll be back to the minimum height of 45. Now the average height would be at the middle of the wind turbine. The average height is 55 meters off the ground. Let me just draw in a horizontal line through 55. I know it's going to be at that average height halfway between these min and max values. So if there's a min at 0 degrees and a max at 180, it'll be at the midline halfway between 0 and 180, which is 90. And then again, halfway between this max and min, between 180 and 360 is 270. And then I can go ahead and connect these points, and then I've got one cycle of this function that shows the height of the tip of this blade right here as it rotates around. Part B says to model the height of the tip of the blade above the ground versus the angle of rotation using a transform sine and cosine function. If I'm going to do that, I'm going to have to solve for A, K, D, and C. If I want to solve for the A value, I just need the amplitude, which is the distance from the midline to the max, or from the midline to the min. It's half the distance between max and min. I can see on my graph that that distance is 10, but we could also calculate it by doing max minus min over 2. My max height is 65 and my min height is 45. Cut that in half, and I figure out that A is 10. K is 360 divided by the period of the function, and period is the horizontal length of one cycle. Well, the horizontal length of one cycle would be from the minimum point to the next minimum point, and that horizontal distance is 360 degrees. So my period is 360, which means my K value is 360 over 360, which is 1. C is the average height. It's the midline. And I already graphed that. It's at 55. But we could calculate it by finding the average of the max and min. So just do max plus min over 2, which would be 65 plus 45 over 2, which is 110 over 2, which is 55. Now, these three parameters are all going to be the same no matter whether we're doing a sine or a cos function to model the relationship between those variables. But the d values, the horizontal shifts, will be different. If I want to do a cosine function, the d value is the x-coordinate of a max. Here's a max, its x-coordinate is 180. So for the d value of cos, I could use 180. But if I want to do a sine function, I need the x-coordinate of where a rising line intersects the midline. So this point right here, its x-coordinate is 90. So the d value for sine could be 90. And now I can just sub in those parameters into my transform sine and cos functions to get two equivalent functions that model the relationship between these variables. And there are the two equations. Hopefully, if you made it to the end of this lesson, you have a good understanding of how trig functions can be used in these types of applications. Make sure you try out the practice questions on Jensen Math, and stay tuned for the next video. Jensen Math!